Transient heat conduction is how the temperature changes as a function of time. And there are 4 different approaches that we can use. The first one is the lumped system approach, then the transient heat conduction approach in large plane walls, long cylinders, and spheres. The third one is transient heat conduction in semi-infinite solids, and the fourth one is transient heat conduction in multidimensional systems. With the previous lecture, we've started with lumped systems. And just to summarize the most important part of the lecture, we've looked at an arbitrary body with a certain mass, Cp volume, and it is at a constant temperature Ti, and at T equals 0, it is exposed to an environment which is at the temperature T infinite with a heat transfer coefficient H, and the body has a certain surface. And then we've derived this simple equation which gives us the non-dimensionalized temperature as a function of time, where B is the time constant. B is equal to the heat transfer coefficient multiplied by the surface area divided by rho, the volume, and Cp. And then the question was, when can we use the lumped system approach? And the lumped system approach can be used by using the Biot number. The Biot number is the resistance ratio inside the body divided by the convection resistance at the surface of the body. So if you look at that sketch, let me just put it on, that I've drawn yesterday. This one is a little bit more neat. If we look at that body, okay, then we see that there are 2 resistances. There's the conduction resistance on the inside, and there's the convection resistance on the outside. The conduction resistance on the inside is a function of L divided by the thermal conductivity, and the convection resistance on the outside is a function of the heat transfer coefficient 1 divided by H. So the Biot number gives us the ratio of the conduction resistance within the body to the convection resistance at the surface of the body. Okay, so it was given by this equation, and that is where it comes from, where the characteristic length can be determined by the volume divided by the surface area. And in terms of using this criteria, we've said that if the Biot number is equal to 1, it would give us an exact solution of a lumped system. That never happens, because if we look at the Biot number, and when we have physical things, it will never happen that any of those 3 terms can be 0. Okay? It can be close to 0, but it can never be exactly 0. So that is the first case. So that never happens. If we look at the Biot number, then there will always be a value for the heat transfer coefficient, L and K, and not one of the 3 can be negative. So the Biot number will always be larger than 0, which means that we can always use this approach to give us an approximate solution. Not an exact solution, but an approximate solution. So, and then the third category is then, when would it give a good result? And it would give a good result typically when the Biot number is smaller or equal to 0. And that only happens sometimes. Okay. Now when is this sometimes? When would that be? Okay. It would be if we look at the Biot number and we look critically at the 3 variables that play a role. The Biot number would give us a small value, which means that we can use the lumped system approach when, firstly, the heat transfer coefficient is small. When the heat transfer coefficient is small. Okay, that is the first case. Then also when LC is small. Okay, which means usually it is a small body. Small body, heat transfer coefficient small. And then thirdly, when K is large. the thermal conductivity of the body is very high. So that is the three different categories for it. So if you look there on the slide, when the heat transfer coefficient is small, when will the heat transfer coefficient be small? If you page back in your textbook at typical values of heat transfer coefficients, then in table 1.5 you had, it was given to you these values of the heat transfer coefficient for different cases. And you will see that typically the heat transfer coefficient is small for free convection of gases. Okay, so when we have free convection of gases, a body in air or in a gas, then usually the heat transfer coefficient would be small. We can see if it's in liquids, then it increases to about 10 to 1,000. Okay, so it's higher. Then forced convection of gases, 25 to 250. Forced convection of liquids, 50 to 20,000. And boiling and condensation, 2,500 to 100,000. So normally the heat transfer coefficient is small for free convection of gases or maybe free convection of liquids. So it could be limited to those cases. So that is the first one. The second one is obviously the geometry. The body must be small. The smaller the body, the better the lump system approach is going to be. And the third one is when the thermal conductivity is high. When is the thermal conductivity high? Again, if you go and look in figure 127 in the first chapter, where the textbook just gave you an overview of typical values, then the thermal conductivity is given here in a graph like this. Okay. And here you can see the thermal conductivity of bodies made from air, carbon dioxide, hydrogen and helium. Their thermal conductivities will be very low. Okay, while on this side we've got copper, quartz, silicon, carbide, etc. So those bodies have high thermal conductivity. Okay. So those are the three criteria that we can use. Typically, bodies with small heat transfer coefficient, which are also small and have a large thermal conductivity. They would give us a very, very good approximation of the lump system approach. Let's think of two different types of bodies that we all know. First type of body is a small ball bearing. Okay. And let's suppose the diameter of it is 1 millimeter. And it is made from stainless steel. It's made from stainless steel and it is exposed to air. Okay. And this stainless steel ball bearing temperature has been increased to 100 degrees Celsius and we put it in air. So this is the first scenario that we're going to consider. And we're going to compare that to one of these big gym balls that you get these days in a gym. The diameter close to about maybe 1 meter. Okay. 1 meter ball. So let's suppose that dimension is 1,000. What is on the inside of the ball? Well, as far as I know, it's air. Okay, it's air. And this is going to be exposed, be thrown into something with water, where this water is circulated around the ball. Okay. And let's suppose the ball temperature has been increased to 50 degrees Celsius, and this water temperature is 0 degrees Celsius. Okay. So two extremes in terms of what we can consider as possible candidates, good or bad candidates for a lump system approach. Okay. Now let's look at the first one, the ball bearing. With a ball bearing, I'm going to make the ball bearing a little bit larger now. I'm going to make it larger. Okay. So because we've got stainless steel, and stainless steel has a high thermal conductivity. Because it has a high thermal conductivity, this resistance term inside the stainless steel is very, very small. Okay. While here on the outside, we've got air. Okay. So the resistance is very, very high. This resistance is 1 divided by the heat transfer coefficient. The heat transfer coefficient of still air is typically maybe 20 or something like that, 10 to 20. So this is going to be a high value and a low value. So that is the one scenario in comparison with this ball, where we now have air on the inside. Now air has a very low thermal conductivity. Because the thermal conductivity is very low, we've got a very, very high resistance on the inside of the body, while on the outside we've got water which is being pumped over this air ball, and its resistance is very, very small. Okay. So two different cases. So if we look again at the definition of the Biot number, which is about the conduction resistance in the body divided by the convection resistance on the outside, then we will see that this Biot number is going to be small and this Biot number is going to be large. Where the Biot number is about the resistance of conduction on the inside of the body divided by the resistance of convection on the outside of the body. Ladies and gentlemen, do you follow? It's simple. Let's do an example. An example is a person is found dead at 1700 hours in a room whose temperature is 20 degrees Celsius. The temperature of the body is measured to be 25 degrees Celsius when found, and the heat transfer coefficient is estimated to be 8 watts per meter square degree Celsius. Modeling the body as a 300 millimeter diameter, 1.7 meter long cylinder, estimate the time of death of that person. Okay, let's do that one. So here's a cylinder. We say this person can be approximated as a 1.7 meter long cylinder with a diameter of 300 millimeters. Okay. And the room temperature in which the person was found is 20 degrees Celsius. And when the person was found, that was at 1700 hours. The temperature of the body was measured to be 25 degrees Celsius. And the heat transfer coefficient is estimated to be about 8 watts per meter square per degree Celsius. What was the initial temperature of the body? Okay. It hasn't been given, but all of us, our temperatures are about 37 degrees Celsius if you are not too sick. About 37 degrees Celsius. Okay, so in terms of this approach, of the lump system approach, we know that we can describe this problem with this equation. So the temperature minus T infinite divided by the initial temperature minus T infinite is equal to E to the minus BT, where B is equal to the heat transfer coefficient multiplied by the surface area divided by rho, the volume Cp. And the Biot number is given as the heat transfer coefficient multiplied by the characteristic length divided by the thermal conductivity K. Okay. So the first thing we need to do is to determine if this would be a good, if we use this approach, would the answer be accurate in terms of a lumped system approximation? So we need to determine the Biot number and see if it is smaller than 0.1. We know we can always use this approach because it will always give us an approximate solution. Not necessarily very accurate, but we can always use it in any case. So, to determine the Biot number, we need the characteristic length. Okay. So the characteristic length is equal to the volume divided by the surface area. Okay. The volume of the surface is equal to pi divided by 4 multiplied by 0.3 square multiplied by the length, and that would give us the volume of the body. Pi divided by 4, 0.3 the diameter square multiplied by the length of the body, 1.7 meters. What is the surface of the body? The surface of the body would be equal to pi multiplied by 0.3 multiplied by 1.7. So it would give us this surface here, but we also have to add this surface and that surface. Okay. So we can actually say it is 2 times this surface. Okay. So it is plus 2 times pi divided by 4, 0.3 square. And if we calculate it, it is equal to 0.0689 meters. So that is the characteristic length of the body. We've got the characteristic length now. The heat transfer has been given. We need the thermal conductivity. Now, what is the thermal conductivity of all of us?
So, Prof, just one thing. Because it falls under the long cylinder category, you not then have to apply what you gave us under the criteria for the characteristic length.
It is not a long cylinder. Okay. It's not a long cylinder. A long cylinder would be a cylinder where usually we do not look at the end effects. So it would be a very, very long cylinder, and the longer the better. Okay. So you are attaching this problem in terms of what would be a better solution, and it's going to come out now that you will see that the Biot number is not going to be smaller than 0.1, so it's going to be an approximate solution. So the long cylinder solution that we're going to do in the next part of the work is going to be a better estimate of the time of death than in this case. Okay. Okay. So coming back to the Biot number, we've got the heat transfer coefficient, we've got that one now. We need the thermal conductivity of all of us. Where do we get that? Well, what we're going to do is we're going to say that 72% of all of us consists out of water. Okay, 72% is water. So therefore, because the thermal conductivity of people, or flesh, or meat, isn't given in your textbook, we're going to use that of water. And we're going to do it in many cases. For example, fruit also. Fruit also, very, very large content of water. And if you don't have the values, then we use water in the meantime. Okay, so it's an approximation. So 72% of all of us is water. And now, getting the thermal conductivity. If you go and look in your textbook, ladies and gentlemen, it's very important that at the end of your textbook there are quite a lot of tables, and you're going to really use it a lot. So you have to know where the information is, and you're just going to know where the information is by using it a lot. And I see many of the students in the test and exam put in actually tabs and stuff like that, because it's easier for them to get to it. So you can also consider doing that. But in any case, if we look at the thermal conductivity of water, If we look at the thermal conductivity of water, you will see it is a function of temperature. Thermal conductivity is water as a function of temperature. So for example, at 37 degrees Celsius, the thermal conductivity is equal to 0.627, while at 25 degrees Celsius, it is equal to 0.598. So the thermal conductivity is a function of time. Which one are we going to use? Which one are we going to use? Okay, what we normally do is we use the average. Okay. See, so we're going to say the average temperature of the body is going to be 37 plus 25 divided by 2, which is equal to 31 degrees Celsius. So we would like to know what is the thermal conductivity at 31 degrees Celsius. Okay. So the thermal conductivity at 31 degrees Celsius from the tables is equal to 0.627 watts per meter Kelvin. And if you look at this equation, you're going to see we also need the density and we also need the Cp. And we do the same for them. So at this average temperature, between where the body started and where it is now, which is 31 degrees Celsius, we are also going to obtain the density and the Cp.
So that thermal conductivity value is exactly the same as at 37 degrees Celsius.
Oh, I see. Okay, right, okay. Okay. Just go and check this value. Yeah. Okay. Understand? Okay. Okay. So I just made an error here with the thermal conductivity. So what it is all about is the fact that we need the temperature, the thermal conductivity, the density, and the Cp value at the average temperature of 31 degrees Celsius. So the density would then be equal to 996 kilograms per cubic meter, and the Cp value is equal to 4178 joules per kilogram. Degrees Celsius. So the properties, we've obtained the properties now. And now we can go and calculate the Biot number. The Biot number is equal to the heat transfer coefficient multiplied by the length scale divided by the thermal conductivity K. The heat transfer coefficient is equal to 8. Okay. The length, the characteristic length is equal to 0.0689, and the thermal conductivity 0.627. So therefore it is equal to 0.879, which means that the lump system approach is just going to give us an approximation. It is not going to give us a good value. It's going to give us an approximation. Okay, let's calculate the time constant B, which is equal to h multiplied by the surface area divided by rho VCP. That is equal to the heat transfer coefficient, which is 8, multiplied by the surface area, which is pi multiplied by the diameter multiplied by the length, the first surface, of the cylinder, this surface here. And now we have to include the two surfaces at the ends, plus 2 times pi divided by 4 multiplied by 0.3 square divided by the density, which is equal to 996, multiplied by the volume. Volume is pi divided by 4, 0.3 square multiplied by the length. That is the one way of doing it. The other way is to say that the length scale is equal to, the characteristic length is equal to the volume divided by the surface. The volume divided by the surface. And here we've got the volume divided by the surface. Okay. So we can say that B is also equal to the heat transfer coefficient multiplied by rho, divided by rho, the length scale, and Cp. And you could have calculated it like that also, much shorter and easier to do it like that. Okay, but in any case, the answer is equal to 2.79 e to the minus 5 per second. Okay, so the temperature, the non-dimensionalized temperature as a function of the time constant is given by that equation. So we are interested at the temperature, or it's given at 1700 hours, minus T infinite is the temperature of the room, which is equal to 20 degrees Celsius, divided by the initial temperature of the body, 37 degrees Celsius, minus again the room temperature, which is equal to 20. Okay, is equal to e to the minus 2.79 e to the minus 5 multiplied by T, from which we can solve that the time is equal to 43,860 seconds. And that gives us 12.2 hours. So it took 12.2 hours before the temperature of the body changed from 37 degrees to 25. So the time of death is approximately 4 o'clock in the morning. Or 5 o'clock. Approximately 5 o'clock in the morning. Okay. Any questions, ladies and gentlemen? The next question, the next problem. Problem 4.14 at the back of the chapter. Problem 4.14. The temperature of a gas stream is to be measured by a thermocouple whose junction can be approximated as a 1.2 millimeter diameter sphere. The properties of the junctions are K 35, rho 8500 and Cp 320, and the heat transfer coefficient between the junction and the gas is 90. Determine how long it will take for the thermocouple to reach 99% of the initial temperature difference. So the thermocouple, 2 wires, and now we've got this point of the thermocouple whose diameter is 1.2 millimeters. 1.2 millimeters. And it is in a gas stream. It's in a gas stream. The heat transfer coefficient is given as 90 watts per square meter degree Celsius. The K of the thermocouple is 35 watts per meter degree Celsius. The density is equal to 8,500 kilograms per cubic meter. Cp is equal to 320 joules per kilogram degree Celsius. Determine how long it will take for the thermocouple to reach 99% of the initial temperature difference. It's a little bit confusing, the question. Okay. But let's make it a little bit easier. Okay. And we can make it easier in the sense that let's try to understand what people normally want to know if they want to take thermocouple measurements. If you want to take thermocouple measurements and you have, for example, a thermocouple point which is at 100 degrees, sorry, no, we've got it, a gas, let's take a gas stream of 100 degrees Celsius. So the gas stream is at 100 degrees Celsius and the thermocouple temperature is at 0 degrees Celsius. Okay. What you're interested in knowing is how long will it take before this thermocouple measures 100 degrees Celsius. And if you are within 99%, then it's already good. So 99% means that we are 1% from the real measurement. So it's about the fact that how long will it take for this thermocouple to measure 99 degrees Celsius. So if we write it in terms of the non-dimensionalized time, then it is about how long will it take for the thermocouple to be 99 degrees Celsius in a stream which is 100 with the initial temperature of the thermocouple 0 to 100. So it is about this 1% uncertainty. So the question is, how long will it take for the thermocouple that if I take a measurement, I know that I'm within 1% of the reading. That is what it means. You follow that? Okay, let's calculate the characteristic length of the thermocouple point. It is the volume divided by the surface area. The volume of a sphere is pi multiplied by the diameter divided by 6. That is the volume of a sphere. The surface area of a sphere is equal to pi d squared. So the result is that it is equal to the diameter divided by 6. The diameter is 1.2 millimeters, so it is 0.0012 divided by 6, which is equal to 0.0002 millimeters or meters. Okay, the Biot number, the heat transfer coefficient multiplied by the characteristic length divided by the thermal conductivity K. The heat transfer coefficient has been given as 90. The characteristic length is equal to 0.002 divided by the thermal conductivity of the thermocouple, which is 35, and that gives us a Biot number of 0.000629. Which is less than 0.1, and that means that the lump system approach is going to give us very good results. The lump system approach is going to give us very, very good results. Okay, so we need to calculate B, and B is equal to the heat transfer coefficient multiplied by the surface area divided by rho Cp and the volume. Okay. Those two can be written as the heat transfer coefficient divided by rho Cp and the characteristic length. The heat transfer coefficient is 90. The density is 8,500. Okay, Cp is 320. And the characteristic length is 0.0002. So it is equal to 0.2022 per second. The time constant. Okay, so let's put it into equation 1. If we put it into equation 1, then that is about the 1% uncertainty. Here we've calculated that ratio. We want to know how long is it going to take before it reaches within 1% of its real value. 0.01 is equal to e to the minus 0.2022 multiplied by t, from where we can solve that the time would be 22.8 seconds. 22.8 seconds. Any questions, ladies and gentlemen? If not, thank you very much and enjoy your weekend.